Hi guys, so in this video we're going to be going into the concept of ozone depletion or destruction. So the first thing we want to understand is, why do we care if ozone is depleted in our atmosphere? Well, ozone is a really common gas in our atmosphere that basically it helps shield UV light from our organisms, so it kind of traps it in there. It's very good at then regulating the quantities that enter our Earth. And it's a bit similar to an oxygen molecule, except it has an extra oxygen. So it's O3 instead of O2. Now, why is ozone being destroyed, really, or depleted? Well, the reason is because of free radical substitution. That's a process that is initiated by the presence of chlorofluorocarbons, or CFCs. So CFCs are chlorofluorocarbons. And it might be pretty obvious based on this word what CFCs are. So we can actually see chloro, then we can see fluoro, and we can see the very obvious one is carbons. So essentially what this means is that chloro comes from the word chlorine, fluoro comes from fluorine, and carbon is carbon. So what does this mean? It means that it has C, F, and Cl are present. So these are the three elements that are present. And this process of ozone depletion typically takes place under UV light. So let's think about CFCs. The CFCs are used typically in refrigerators and other stuff. That's why it's in such high demand. But however, this can also lead to the destruction of ozone, which is not good for our environment. So if we have a CFC, let's take this CFC over here, CCl2, F2. Let's take this CFC over here because it has all of the crucial elements. So under the presence of UV light, let me just add in purple, UV light, it can be transformed into CClF2 with a dot plus Cl. So this is all in gaseous state, just to clarify. So let's first understand why this happens. So I'm going to go into this quite briefly because there is another video that we do cover homolytic fission and free radical substitution in. But in this, let's just try and unpack what's happening in this specific scenario. So if we draw out the CFC molecule, so we have C, then we have Cl, Cl, F, and F. That's our molecule. So we have two types of bonds. We have CCl bonds and CF bonds. So the bonds that are going to be broken are the CCl bonds in this case, because the CCl bond is weaker. Given that the electronegativity difference between C and F is higher, it is therefore a more polarized and stronger bond. However, the C and Cl bond is weaker in that respect. So we're going to have this bond be destroyed. Now, the reason why we get a chlorine radical instead is because chlorine is more electronegative than carbon, which means the electrons are more compelled to go towards the chlorine. So our chlorine radical over here, sorry, I just forgot the dot, is going to be the one that receives all the electrons and breaks away from this atom to give the free radical that we have. So C, Cl, F, F, and then the free radical. There's an extra electron that just doesn't have anyone to bond to right now. And Cl. This is under UV light. And this process is called homolytic fission. Actually, in this process, it really is heterolytic fission in the sense that chlorine is the one that got all the electrons, we can see. But the thing is, this is also the first step of free radical substitution, known as initiation, which is covered more later. Anyway, so the more important thing to notice is that the chlorine radical is on its own now. And so what happens to it? Let's just erase this part over here, just to free up a little more space. Right. So let's go back to what we have now. So what we have is Cl, a Cl radical, and we have our other radical with CClF2 and the radical. However, we're going to take our Cl radical, known as a chlorine radical, because it has an unpaired electron, and add it to an ozone molecule. So it's going to go and react with an ozone molecule, and it's going to produce ClO dot plus O2. So I just want to clarify that if it's not clear already, the radicals are when there's one electron that is not bonding. So usually you might see a lone pair. Let's say you had oxygen. Oxygen has 3 lone pairs. However, they are pairs of electrons. When a molecule has an odd number of electrons and that is left on its own, let's say you can take nitrogen, which has 5 electrons around it, and you have one that's unpaired like that, it is known as a radical. So in this case, the chlorine atom has 7 different electrons around it, and this radical over here, that's not being paired with anything. All right, so now you add it to an ozone molecule, and this time the chlorine is going to bond to one of the ozone molecules, one of the oxygen atoms in the ozone molecule, and take it away. It's going to steal it away to form a chlorine and oxygen radical over here, and that's going to remove the ozone and produce oxygen because one of the oxygens is removed. So that's the next stage, and this is an example of the propagation of radicals. However, there is another example of propagation of radicals where the ClO molecule that we have here, the radical, reacts with another oxygen radical to form Cl radical and more oxygen gas. So these are just examples of how the radicals are kind of propagated along. And in this respect, this is why it's known as propagation, because it keeps getting carried on. So in this respect, we're able to get, these radicals are able to displace many different oxygen atoms from ozone atoms, molecules, and therefore create a lot of destruction in terms of the ozone. So it is actually said that one molecule of a CFC can catalyze the breakdown of up to 100,000 molecules of ozone, just because the propagation of radicals is such that many different ozone molecules can be disrupted. So there is also evidence that nitrogen oxides can also result in the decomposition of ozone through radical mechanisms, but that's another example only. The point is, you want to know that there are some things like CFCs and nitrogen oxides that can catalyze the process of ozone depletion, and that these radicals continue to react and steal away atoms and therefore cause great changes in molecules, including ozone. And this is a very harmful thing and therefore shows that CFCs can be very detrimental to our environment. Anyway, I hope that process just helps simplify it down.